Welcome to The Explainer. Today, we're diving into the one component that can make the difference between a computer that flies and one that, well, really doesn't. Yep, we are talking all about random access memory, or, as you probably know it, RAM. So let's kick things off with a feeling I'm pretty sure we've all had. You know the one. You're deep in a project, you've got like a million browser tabs open, maybe a spreadsheet, some music playing, and then boom, everything just grinds to a halt. That super frustrating lag, well, that has everything to do with RAM. Okay, so the answer to that slowdown is all about this thing called RAM. And to really get what it does, the first thing we need to do is break down its name. What does random access actually mean?
So what exactly is RAM? Well, at its heart, it's basically a temporary, super fast storage area. And honestly, the best way to think about it is like a workbench. It's where you keep all the tools and all the files you're using right this second. Your hard drive, that's the giant filing cabinet in the back room. It stores everything for the long haul. But RAM is your active workspace. And it's pretty simple. The bigger your workbench, the more stuff you can do at once without making a huge, slow, cluttered mess.
And this right here perfectly explains that whole random access part. Picture it like a book. If you need to find something on, say, page 247, you just flip right to it, instantly. That is random access. Your computer can grab any piece of data from any location in RAM in pretty much the exact same tiny amount of time. Now, the opposite of that is serial access, which is kind of like an old cassette tape. To hear your favorite song, you have to sit there and fast forward through everything else first. You see the difference? That's what makes RAM so incredibly fast.
Okay, so how is RAM actually built to pull off this incredible speed? Let's, pop the hood and take a look inside the memory matrix itself. So at its most basic level, RAM is just this massive, massive grid of storage cells. I want you to picture a giant sheet of digital graph paper. Each tiny little square on that grid is a binary cell. It's basically a microscopic switch that's either on or off, representing a 1 or a 0. And that right there is the fundamental building block of, well, all digital data.
So how in the world does the computer find one specific bit among billions? Well, as you can see here, every single piece of data gets its own unique address. It's kind of like a digital mailbox system. The computer doesn't have to search around for anything. It just goes directly to the address, say address 1023, and grabs the data it needs. This super precise addressing system is the real secret to its random access speed.
And the sheer scale we're talking about here is it's hard to even wrap your head around. The number of possible addresses is all based on powers of 2. So for just one single gigabyte of RAM, you need 2 to the power of 30 unique addresses. That's over a billion individual locations, a billion digital mailboxes, and every single one is instantly accessible. The scale is it's immense.
But, not all RAM is created equal. It's definitely not a one-size-fits-all kind of deal. It actually comes in 2 main flavors, and each one has a very different and very specific job to do inside your computer. All right, so the 2 main types are SRAM and DRAM. First up, you've got SRAM, or static RAM. As you can see, it's way, way faster. But, and this is a big but, it's also a lot more expensive and complex to make. Because of that raw speed, it's used in really small amounts for the processor's cache. Think of it as a tiny, lightning-fast memory buffer right next to the brain of the computer. Then you've got DRAM, or dynamic RAM. It's simpler, it's cheaper, and you can pack way more of it into a small space. And that makes it absolutely perfect for your computer's main memory. You know, the 8, 16, or 32 gigabytes you always see advertised? It's a classic engineering trade-off, right? Blistering speed for a high price versus massive capacity for a much lower cost.
So how does all this work in practice? I mean, moment to moment, RAM is constantly doing 2 basic things over and over again: reading data and writing data. Let's break down exactly how that happens.
Okay, so when your computer needs to save information to RAM, like even when you just type a single letter in a document, it performs what's called a write operation. And it's a really simple 3-step dance. First, it sets the address where the data needs to go. Second, it applies the actual data bits. And third, it hits the write signal, which basically tells that specific spot, hey, store this new information right now.
And getting that data back out, that's even simpler. It's called a read operation. The computer just applies the address of the data it's looking for, and then it activates the read signal. And that's it. The data at that specific address is then instantly available for the processor to use. And these 2 simple cycles, read and write, are happening billions of times every single second. It's wild.
But with billions and billions of these things happening every second, stuff can go wrong. A bit can just flip by mistake. So how does this absolutely critical piece of hardware protect itself from these tiny little digital glitches?
Yeah. Let's just think about that for a second. What actually happens if a single bit, just one out of billions, flips by mistake? Maybe because of a random cosmic ray from space, or a tiny little power fluctuation. A 1 suddenly becomes a 0. That single tiny flip could crash a program, corrupt a file, or even cause a total system failure. Now, for most of us, that's an annoyance. But in high-stakes places like servers or scientific computers, that's a huge, huge problem.
So, the solution is this really special type of memory called error-correcting code, or ECC-RAM, and it is a brilliant system. For every chunk of data that gets stored, ECC-RAM generates and stores a few extra check bits right alongside it. You can think of these extra bits as like a super sophisticated security guard for your data.
Now, here's the really clever part. When the data is read back, the ECC logic recalculates those check bits. If they don't match the original ones, it knows, uh-oh, there's an error. But it gets even better. Based on how they don't match, it generates this unique code called a syndrome. And this syndrome doesn't just, raise an alarm. It acts like a map, pinpointing the exact bit that flipped, which allows the system to correct it on the fly, instantly.
All right, so let's do a super quick recap of the key takeaways. First, RAM is your computer's temporary high-speed workbench. Second, random access is the magic sauce that means it can grab any piece of data instantly. Third, it comes in two main types, super-fast SRAM for the processor cache and high-capacity DRAM for main memory. And finally, for those really critical applications, ECRAM is there to find and fix errors as they happen.
And that brings us to one last thought. From AI to virtual reality and beyond, our hunger for faster, denser, and more reliable memory is just growing like crazy. The principles we've covered today are the foundation, but this technology is always evolving. So the question is, what's the next generation of this essential digital workbench going to look like? Thanks for joining us for this explainer.